Okay, so what we've got here is an integral that I've been seeing online, and I'm going to give it a go and see if we can solve it. So before we jump into it, first thing I want to note is that this up here is an infinity, so we've got to just check it converges. So by looking at it, we can see that it probably will, and the reason why we know that is inside here, as x approaches infinity, 1 over x is going to approach 0, and so we're going to have arctan of 1 over x is approximately equal to 1 over x at that point. Because obviously when x is small, we have our small angle approximations. So it looks like it's going to converge. I'm not really going to bother rigorously proving that it does, but what we know is that the graph looks something like this. It's a very bad graph. It should asymptote towards 0. And obviously this is going to be pi over 2. So first things first, we can do this in two steps. It will look nicer because we want to get this inside and somehow change it into a tan theta. So we can do the sub straight away. You guys might prefer to do u equals 1 over x and then u equals tan theta. But essentially they're the same thing. It's just making the differential easier to work with. So first things first, we're going to sort the bounds. As x approaches 0, tan theta approaches infinity, which means that theta approaches pi over 2. As x approaches infinity, tan theta approaches 0, so theta approaches 0. That's it really for that bit. Now we need to use differentiator. I'm going to do it the physicist method, where I don't write d theta by dx, I just write dx. These are common differentials that we should know, so we can just quote them. And then all we have to do is sub this in. So our upper bound, as we found here, is going to be, sorry, that's our lower bound. I'm going to have pi over 2 at the bottom. And then our upper bound is going to be 0. That looks a little bit weird because it's bigger in the bottom, but it will sort itself out and you guys will see how that works. When we're sorting our differential, this here is going to be negative tan squared theta dx equals sec squared theta d theta. And the reason for that is I'm just subbing in this into this 1 over x squared. This is useful because it gives it us all in terms of theta. Sometimes you don't want to do stuff like this. You don't want to force the subs. You want to see if stuff's going to cancel out first. But in this case, it's not going to cancel out. So what we've got is arctan of tan theta squared times by negative sec squared theta over tan squared theta d theta. This minus here means that we can flip our bounds, so I'm going to do that as I simplify the rest of the integral. This whole bracket is just going to be theta squared, because arctan of tan, the inverse functions, they're just going to, the tan bits is going to cancel, we're just going to get theta squared. So we're going to have theta squared, sec squared theta over tan squared theta d theta. Now, what we can do with this is first off put it into terms of sine and cos. So theta squared 1 over cos squared theta over sine squared theta over cos squared theta. And these causes are going to cancel out. We can times 3 by cos squared if you want to, but they just cancel. And then we've got theta squared over sine squared. That's going to be theta squared cosec squared theta. I like to write my cosec's CSC, just because it makes it smaller and 3 letters like the rest of them. So that's how I'm gonna have it. Now, one thing we can do here is change this into a sec by using the bounds, although we don't really need to do that, it'll work either way. Because what we're going to do is we're going to do integration by parts. And in fact, it will turn out nicer if we don't change it into sec. So I'm going to call this our U. Remember our acronyms: late, log, algebra, trig, exponential. We have algebra, that's our theta squared, so that's our U. So U equals theta squared, du equals 2 theta d theta, dv equals cosec squared theta d theta, v equals negative cot theta d theta. This again is just something we should know. We know that d by d theta of cos theta equals cosec squared theta. Sorry, negative cosec squared theta. So we just times 2 by -1, and that's how we get it. So our integral is now equal to uv, so negative theta squared cot theta, subtract integral of v du. These negatives cancel, so I'm going to make them plus. Now the thing that we can notice about this is that we've got theta squared cos theta over sine theta. When we've got pi over 2, I'll move over here a little bit, theta equals pi over 2, cos theta equals 0, so that's going to be 0. And when we have theta equals 0, this might look like we've got an asymptote because sine of 0 is 0, but actually we're left with essentially limit as theta approaches 0 of theta squared cos theta over sine theta. The cos theta is going to be 1 here, so we don't really need to bother about that. Just kind of scribble it out. And when theta is small, we have sine theta is approximately equal to theta. So that's what we've got. So we've got limit is theta approaches 0 of theta, so that's just going to be 0. So in fact, this entire first bit is just going to be equal to 0. So this is our new integral. So we've got 2 from 0 to pi over 2 theta cot theta d theta. I want to do parts again. So same thing as last time, used our late acronym. U equals theta, du equals d theta, dv equals cos theta over sine theta, v equals ln mod sine theta. Oh, d theta there. So we've got, I'm going to forget about the 2 for now, but I will remember it later, don't worry. So we've got theta ln mod sine theta from 0 to pi over 2, subtract integral from 0 to pi over 2 of ln sine theta d theta. So let's start with this bit again. When theta equals pi over 2, sine theta equals 1, and ln of 1 is equal to 0, so that's going to be 0 for the first bit. Theta equals 0, we've just got 0 essentially times by ln of 0. Again, that approaches infinity. It's a bit harder to show, approaches negative infinity. It's a bit harder to show why that's equal to 0 this time and why it doesn't diverge. But you'll have to take my word for it. It converges to 0. You can kind of just think of it as 0 times by negative infinity, and the 0 is more powerful. So that's just going to be 0. Although this is not rigorous, so yeah, feel free to show it rigorously if you want. So this whole thing is going to be 0 again. Now this is actually a decently famous integral. The first thing I want to do is use something called King's rule, which means that this is what King's rule states. And what this does is it means that if we have the bounds from 0 to pi over 2 like we do, and we've got a sine in our integral, we can change that to a cos. So that's what I could have done all the way up here, where I said I could change this into a sec. That's using this rule here. And the way that we do it is we do a sub u minus pi over 2, or pi over 2 minus u, both of them work, equals theta, as theta equals 0, u equals pi over 2, theta equals pi over 2, u equals 0. So our bounds are going to flip, but our differential, because of that negative there, it flips them back. So that means that this integral here, ln of sine theta, is the same, let me label this as I, as integral from 0 to pi over 2 of ln of cos theta. And you can think about that graphically if you want. This is going to be left one for ln of sine theta, and the right one for ln of cos theta. Ln of sine theta is going to look like that, but it's going to meet at around pi over 2 at 0. Ln of cos theta is going to look the opposite, but again, it's going to be the same thing. So these are just reflected around the line pi over 4, which is why they're the same, because the area is sine and it's the same underneath for both of them. So what we're going to do now is take this integral and add it to this one. And that's going to get us 2I equals, which goes from 0 to pi over 2, of ln of sine theta cos theta. Using our log rules, we can multiply them together inside. This here, we're going to want to change this into terms of sine 2 theta. So sine, I'll use x here, 2x equals 2 sine x cos x. Sine x cos x equals sine 2x over 2. So 2, that's our integral, is going to be the integral from 0 to pi over 2 of ln of sine 2x dx. Although I suppose I should keep that a theta, shouldn't I? It doesn't matter though, it's a dummy variable. Subtract the integral from 0 to pi over 2 of ln 2 d theta. This is just pi ln 2 over 2. That should be quite obvious. Now this here looks very similar to our original integral, doesn't it? So this is kind of like screaming at us that we want to do something cyclic. So if we do u equals 2 theta, we get du equals d theta 2 d theta. And our bounds are going to go from when 0 goes to 0, pi over 2 goes to pi. I'm going to get the integral from 0 to pi of ln mod sine u times by du over 2. So half of the integral from 0 to pi over 2 of ln of sine of u du. Now going back to the graphs, I'm going to sketch this very roughly. You know, the one pi over 2 is here. This is y, this is u, and we've got the function y equals ln sine u. This is pi. This is obviously 0. So sine of 0 and sine of pi are both 0. Sorry. Yes, they are. Then ln of 0 is negative infinity. So we're going to have something that looks like this. It's going to come back down again on the other side. That's a really bad sketch. But in reality, this area and this area are exactly the same. So rather than having the integral from 0 to pi over 2 of y du, we can have 2 lots of the integral from 0 to pi over 2 y du. And those are going to be the same thing in this case. So let's do it. So a half of 2 lots of the integral from 0 to pi over 2. Now what we've done here can be done more formally with something called Queen's rule, which, as you may notice, goes hand in hand with this, which is King's rule. And they're both very useful for trig integrals. So this 2 and this 2 cancel, and then what we're left with is inside here. This is what we've defined as I, isn't it? Up here. So going back to this, we have 2i equals I minus pi ln 2 over 2. So I equals negative pi ln 2 over 2. And then all the way back up here, where is it? Yeah. This 2 and this negative. That's what we need to remember and bring down. So we want to find negative 2i. And then, so negative 2i is just pi ln 2, which is the answer to our integral. So integral from 0 to infinity of arctan 1 over x squared dx is going to equal pi ln 2, which I believe is about 2.77, although don't quote me. So I hope you guys found that as fun as I did, because that was a very nice integral.